Welcome to week 4. This week we're going to be talking about polynomial functions, their graphs, and how to solve for their roots or their zeros. Now when we have a polynomial function and we graph it, where it crosses our x-axis, or where y equals 0, that's where we're going to find our answers or our zeros to those problems. So think about a quadratic, which is a simple polynomial to the second power. It's going to come down in a big U shape, right? Or reversed U shape. It's going to at most cross my x-axis in two places. So the degree of the polynomial will tell us how many roots that we are looking for. There's some helpful charts in your book on page 263 and 265. I have them copied here, but really in your book they're much clearer and easier to understand probably. But the first one over here talks about, right here, talks about the properties of these polynomial functions. They need to be continuous. They need to not have any sharp corners. They need to have the real zeros like we talked about to the nth degree. That means if my polynomial is to the second power, then I will have at most 2 minus 1 turning points, so that's 1, and at most 2 roots. So that nth is talking about what degree my polynomial is up here. Okay, and it's going to increase or decrease as I get further and further away from the origin. Here on the other chart, there's just some things about what's the behavior going to be of these. Is it going to point upward or downward? Is it going to start from the left and go up to the right, or start at the left that way and go downward to the right? And there's some criteria. It just makes it a little easier to graph if we can follow some of those shortcuts. The next thing that it talks about in the book is, as far as polynomial functions, is how to do some polynomial long division. Now this happens to be a favorite of mine. I know that sounds very bizarre, but it really is. I think it's very enjoyable. So here we have this polynomial, and we're dividing it by this polynomial, setting it up just like long division that you learned back in the 4th grade. We're going to look at the first term. So this x here and this number here, this term, how can we change that x into a 3x squared? Well, we can multiply it by 3x, and that is what we do. We put the 3x there, we multiply it, and then we write it down right below. We multiply that 3x also by the 1, and that comes in here. Now, if you remember back to your long division days of just number on numbers, we then are going to subtract this line to take it away from what we have originally. So we'll have to change the sign on both of those things. This cancels out. I don't have to worry about that anymore. But I do have 5x minus 3x, which that is where I get my 2x. And I bring the next term down. I don't know why I find this kind of relaxing, but I find this not difficult, but yet it looks pretty impressive, which is kind of fun. So now again, I'm going to look at the first term that I'm dividing into, and the first term out here in my divisor. What do I need to multiply that x by to give me my 2x? Well, up here we have chosen 2. So again, 2 multiplied by my x, and I write it down here. 2 multiplied by my 1. I know you won't be able to read this line, but I'm going to put it right here. Sorry, that 2x goes there. And we put the 2 there. Now I subtract again. Subtract, subtract, that goes away, and I end up with 4. I have a remainder because x plus 1 will not go into 4. So that is simply my remainder. If I were to multiply this back in, I would have to multiply that remainder. It would look like this: 4 over the divisor, x plus 1. That is what my remainder would look like. So I would have this factor, and this factor, right, my remainder factor. So that's how we do polynomial long division. Now when I am going to work a lot of these problems, this is rather tedious. So we have developed, someone developed the synthetic division. Some students just love synthetic division. It's fine, but I really like the long division, and so I'm not as big a fan of the synthetic division. So how do we set up a synthetic division? Well, this is number 57 from the book. I wanted to show you the example without me writing all these ones and zeros, because that would get quite tedious for you to try to figure out. This line right here, You can see my mark there. Maybe not. I didn't turn on the pencil thing. It takes a minute. Okay. Right there. Comes from this polynomial. I have a 1 as a coefficient for my x to the 5th, but I do not have these terms, x to the 4th, x to the 3rd, x squared, or x. That's why I have zeros. They're placeholders. And then that last one comes from that one over there. So that is what I am dividing. What am I dividing it by? I'm dividing it by this. When we have it written in the x plus 1 form, then I take it as a minus 1 to divide. Remember, if I have x plus 1 as a factor, the root is really x minus 1. So I am really dividing by the root here, or the answer, or the 0, whichever way you like to look at it. So what do I do first? Well, I'm going to bring down my 1, multiply negative 1 times 1, and write it up there. Then I do that bit of math, bring it down, multiply, and bring it up here. Bring that down, multiply, and bring it up here. And on we go, right? Since I have lots of 1s and 0s, it gets a little tedious. Multiply negative 1 by negative 1, I get positive 1. Bring it down. Positive 1 times negative 1 gives me negative 1. And then I actually have a number to add here, and I get 0. So 0 is my remainder. This goes in perfectly. It goes in exactly right. What do I have left? What is the answer, and how do I read it? The answer is read. Let's see if I can erase the scribbles. The answer is read by looking at these 1s and 0s that I have left down here. This is my answer right here. And it shows up with the x's right there. So I have x to the 4th and a negative x to the 3rd. That goes down to that, that. Hopefully you can see how that is a correlation. And I have no remainder. Now what's the real application of this? An interesting thing that we can do once we have the synthetic division down for finding roots. Here's another couple of examples, and it's going to show this kind of remainder theorem idea. So if we have a function, p of x, and we have this function right here, okay? I want to find p of negative 3. Well, yes, I could plug in negative 3 in each of these places where the x is, and in fact that is what is done in b, right in here. I am plugging in negative 3 to find out what my answer is. Or I can do a synthetic division, which a lot of students find easier than doing all of the powers down below. I can do a synthetic division using that negative 3 as my divisor, and what I come up with as the remainder will be the answer, will be that function evaluated at negative 3. That is pretty awesome. If you think about it, I hope that that sinks in. But so how do we use that? Well, you actually are going to be able to evaluate these long polynomials for a certain number just by doing that process of synthetic division and looking at the remainder. That's the remainder theorem tells us we can do. Okay. I think that's probably it for this. Let's stop there for this video. I know that I just give too much information sometimes at once, and it's a little bit confusing. So that's great. I'll see you in the next video.